The matter that we can see, and of which we are made, represents 4% of the total composition of the universe. The remaining 96% is made up of two substances that until now no one knows what they are or where they come from. These substances are called dark matter and dark energy. But how do we know that they exist if we don't know what they are? As we will see in a moment, their existence can be verified in many ways. Not everything that the universe contains emits visible light. It also emits infrared light, ultraviolet, microwave, X-rays, and gamma rays. This electromagnetic radiation is emitted from everywhere. If we know how to capture it, we can see all the hidden wonders of the universe. But despite everything, there are still a lot of things that are there that we cannot observe. How do we know there are more things? Because of the gravity they exert on other objects. If we use our most advanced telescopes and count the amount of matter that we see, the result is that there is very little matter in the universe. There are hundreds of billions of stars in a galaxy. As stars are very massive, they represent the largest mass in the stellar system. So, if we count the stars and we associate a mass with each star, if we don't consider its planets, moons, asteroids, and comets, we don't make a big mistake. So we count all the stars in the galaxy. We associate them with a mass according to their luminosity, and with that, we will know what the mass of the galaxy is. Now, we look for all the galaxies in a certain region. We count the stars in each galaxy and assign them a mass. As we already know the mass and the total size of the region, we can know its density. We compare this density with the critical density of the universe. The critical density determines the exact density for which, if the universe is denser than this density, the universe will expand for a time, but eventually, the gravitational interaction of all the matter in the universe will force it to collapse. If the density of matter in the universe is less than the critical density, then the universe will expand forever. When comparing the density we obtained earlier with the critical density of the universe, the result is that this density is 0.3% of the critical density of the universe. According to this, the space of the cosmos is almost empty. If we now try to form the structure of the universe using only the matter that we observe, we will achieve nothing. What the researchers did was add enough matter to their theoretical models, enough to get the structure we observed. This matter that was artificially added to the theoretical models to make them work is known as dark matter. It was called dark matter because it doesn't interact with light. It is practically invisible. The question that immediately arises is whether this dark matter could really exist, and whether there was any indication that this matter was real. To everyone's surprise, the answer is yes. This evidence was seen first, a long time ago, in galaxy clusters and then in galaxies, but not much attention was paid to it. Galaxies are pure gravitational objects, that is, only gravitational interaction and inertia intervene in them. In 1933, the Swiss physicist Fritz Zwicky analyzed the velocities of certain galaxies in the Coma cluster. He found that many galaxies were moving at extremely high speeds. At these speeds, the cluster should disintegrate, and all the galaxies should shoot out due to its centrifugal force. On the other hand, there is solid evidence that these clusters are stable configurations. So for this to exert a greater gravitational interaction that compensates for the centrifugal force of the movement of the galaxies around the cluster must contain non-luminous matter yet detected, thus achieving that this matter keeps them in balance. In the late 1970s, Vera Rubin and colleagues obtained the rotational curves of 10 spiral galaxies of different types. For the galaxy to be in equilibrium with its rotation, the gravitational force of all these stars must be the same as the centrifugal force of their rotation. To find out its centrifugal force, Vera Rubin used the redshift of the motion of the stars that enter and leave the galaxy due to its rotation, being able to calculate with great precision the tangential speeds of the stars. Vera Rubin compared the results of the speeds obtained according to the gravitational force and the result obtained with the redshift. What she found is that both observations had a marked discrepancy with each other. Stars at vastly different distances from the center of the galaxy rotate with the same angular velocity, and the distribution of luminous matter indicates that this velocity must decay rapidly the further away a star is from the center of the galaxy. Rubin rightly thought that there must be some form of dark matter in these unique regions, located far beyond the visible edge of each spiral galaxy. In fact, dark matter forms a kind of halo around the galaxy. From one galaxy to another and from one cluster to other, the discrepancy between the mass of visible objects and the average total mass of the universe revolves around 6. That is, cosmic dark matter has a mass about 6 times greater than that all visible matter. In recent years, new studies have shown that most dark matter cannot consist of ordinary non-luminous matter. Could dark matter be black holes? No, because we will have detected these numerous black holes based on their gravitational effects in nearby stars. Could they be dark gas clouds? No, because they will absorb or otherwise interact with the light from the stars behind, which dark matter does not. Could they be intergalactic planets, asteroids and comets that do not produce their own light? No, because it is unlikely that 6 times more mass is formed on planets than stars, since that will mean the existence of 2 million Earths for each star in the galaxy. In our solar system, asteroids, comets and planets account for a measly 0.2% of the solar mass. Therefore, dark matter does not simply consist of matter that turns out to be dark. It is something else entirely. Dark matter exerts gravity according to the same rules as ordinary matter, but it hardly does anything to detect it. The term dark matter presupposes the existence of a type of matter that has gravity, and that we do not yet understand. The existence of dark matter does not derive from a mere assumption, but from the observed effects of its gravity on visible matter. So the effects of dark matter are real, we just don't know what it is. Apparently, it does not interact by the strong nuclear force, nor has it been observed to interact by the weak nuclear force. It does not appear to interact with the electromagnetic force, and does not absorb, emit, reflect, or scatter light. It does, however, exert gravity, to which ordinary matter also responds. And that's it. After all these years of research, it has not been seen to do anything else. As we said at the beginning, baryonic matter, that is, the visible matter and from which we are made, only represents 4% of the universe, and dark matter represents 23% of the universe. So what is the rest of the universe? The surprise came in the late 90s. But first, let me explain an interesting phenomenon of the stars. When a star's fuel runs out, the star ends its life in a huge explosion, called a supernova. Depending on various factors, the final luminosity of the explosion is quite different and variable. If the final mass of the star does not exceed the limit of Chandrasekhar, the star ends up in a state called a white dwarf. But if the final core of the star exceeds this limit, the star ends up as a pulsar or neutron star. Binary systems abound in the cosmos, that is, stellar systems with 2 stars, which revolve around their center of mass. In fact, these systems are more common than lone stars like the Sun. Sometimes it can happen that, in a binary system, one of the stars runs out of fuel before its companion. It is also common that the core of the star that ended its fuel first does not exceed the Chandrasekhar limit and ends up as a white dwarf. When this happens, because the white dwarf has a very intense gravitational field, it begins to swallow its partner. If this continues, there comes a time when the white dwarf grows until it reaches the Chandrasekhar limit, which causes the white dwarf to destabilize and collapse again. The resulting explosion destroys the white dwarf entirely, only that now we know that it will collapse precisely with the mass given by the Chandrasekhar limit, 1.4 solar masses. If we know the mass of the collapsing star, we will know how bright it is. This type of supernova, where the luminosity of its collapse is well known, is called Type 1a supernova. This is extremely useful, because if the luminosity of its collapse is well known, we can know its distance. Once astronomers learned to recognize Type 1a supernovas, they had the golden key with which solved the riddle of determining precise distances in the universe. After measuring distances in the nearest Type 1a supernovas, they could calculate distances much greater than other Type 1a supernovas simply by comparing the luminosity of relatively close and distant objects. Two teams of Type 1a supernova observers competed hard to come up with a new Hubble diagram, the key cosmological graph that represents distances of galaxies versus the speeds at which they are moving away from us. The result was that Hubble's law and the slow expansion of the galaxies did not occur. On the contrary, these two groups independently found that the further away the galaxies were, the expansion speed was greater, contrary to what it should be expected. That is, the universe is expanding faster and faster. What caused this extra expansion? The main culprit that fits the facts is dark energy, whose existence corresponds to a non-zero value for the cosmological constant. Matter tends to slow down the expansion of the universe due to the pull of gravity. The higher the density of matter, the slower the expansion will be. However, dark energy does something else entirely. Unlike matter, whose attraction slows the pace of cosmic expansion, dark energy has a curious property. It causes space to expand, thereby accelerating its expansion. As the space expands, more dark energy is created. The new dark energy causes the cosmos to expand even faster. Again, the fundamental question arises: what is this dark energy that acts repulsively against the rest of matter? We don't have the answer. The worst thing that could happen is that physicists discover that dark matter and dark energy do not consist of matter or energy at all, but of something else. Could it be the manifestation of forces from another dimension, or of a parallel universe that intersects with ours? We will see that in the next video. If you liked the video, do not forget to share it and subscribe to the channel if you're not already, and I will see you in the next video. Bye. If you want to support the channel, subscribe to Patreon, where you can also see original short films and science fiction series, exclusive videos, and the possibility of winning amazing prizes. All relevant bibliographic reference and links are in the video description, and thanks for watching.